Hi there, welcome back to the channel. Welcome to the second video in the Back to Basics series of tube radio restorations. What I'm trying to do here, as I mentioned in the introduction in the last video, is I want to go into a lot of detail into every little step that I take in restoring a radio. The idea is that as you go along, you learn techniques and you sort of glance over them. Some people don't know what you're doing, and my idea here is to try and really focus on stuff that I've normally lately just sort of glanced over it and not really explained what I was doing. And this doesn't help, or that does not help, if you're trying to learn the basics of restoration. Now, I went through the same procedure. I learned from a lot of people. I had to go back many times, find different versions of the same job or the same task till I figured out what they were doing. I'm trying to make it simpler for those who want to learn the process. Now, we need to make it simpler. We need to get more people doing this. You know, a lot of the restorers are just phasing out. And that's a great shame, because these radios are going to last for many more years. And if we restorers don't keep up, what's going to happen? One of these days, they'll all end up in the rubbish dump. And that's a great shame. So in this episode, I'm going to go into the start of the restoration itself, starting with the power supply. I hope you get something from it. Enjoy the video. But before I carry on, I just want to thank the sponsors of the video, PCBWay. You can find them at PCBWay.com. And this is the company where I get all my PCBs for the projects that I do and share on this platform. You'll find a huge range of PCB types. There are also 3D printing services that I've used recently to get some gears for one of the radios that I was restoring. Especially useful is the fact that you can get both filament and resin prints. Very good quality. The prices were great as well. And one of the services that I haven't paid that much attention to, although I'm part of it, is the shared projects section. And here you'll see projects that many creators have uploaded, including myself. And it's as easy as finding the project you want. Here's an example of the supply board for the DIY tube tester that I did. I've got quite a lot of projects on here. You just have to follow the videos that I post, and I usually put links straight to the share page. If you want to get these boards, all you do is you add to cart and everything is there to make it easier for you to order. So whether you're looking for PCBs, for CNC machining, 3D printing, shared projects, whatever you want, go to PCBWay.com. You'll find something for your needs. This is really where everything starts, the power supply. And what you're looking at now is really the heart of the power supply, which is the power transformer over there. Most of the time this thing's on the top. In this particular radio it's at the bottom, but it's not difficult to identify. It's a massive piece of iron. And before that, we've got a few things that we need to look at. And believe it or not, it actually starts at the plug. In this case, it's a European plug, non-polarized. Unfortunately, we don't have the ability to polarize here, so we don't really know what is live, what is neutral, because this thing fits in both ways. Unfortunate, but that's the way it is. And then at the top here, we've got a voltage selector there, which says 240, 220, 150, 115 and 110, depending on which country you're in and depending what mains voltage you use. You've got the fuse. In this case, it's one fuse. We have here the selenium bridge rectifier, which we'll look at in more detail in a minute. And of course, on the underside, we've got that dual filter capacitor, which is what makes this AC converted to DC ripple-free. But that's all glossing over, because we've really got to look at this in a lot more detail. As I showed in the previous episode, what we have here is the full schematic, and we can break it down, or rather simplify it, till we have the part that we're interested in, which is this part over here. Now, the power supply is not strictly just this section over here, because we actually have all this in red showing you where the supply goes to, and it goes through switches, and it goes through dropping resistors, and it goes to everything else. But the way I normally look at this is I look at the primary source of the DC power, which is this point over here. And to do that, I'll hide everything else, which means that I'm left with this section alone, which is a lot simpler. And of course, this part here is what I said goes for, it supplies a phonograph, a phono record player, if this was in a different cabinet. And we can hide that as well, which means that we reduce our circuit of interest to this that you see on the screen right now. And that makes life a hell of a lot simpler. And we can look at this in stages. Everything we see here on the screen, we can quite easily identify on the radio itself. And that's the first thing we're going to do. We've got our AC mains over here, which is the socket. And we can see here that it goes into a fuse. That's our fuse over there. We can also see that it then goes to the primary of the transformer, which is that guy over there. If you have live coming in here, when you switch it off, it goes off. If you've got live coming in here, you've actually got live power all the way here till the switch. If you've got live and neutral, it means that live is going in there, going through the transformer, coming out of these various points over here to the switch. So this side of the switch will actually have live connected to it, and it'll be at the full 200 or whatever volts, or 120 volts if you're in the States, until you switch it on. On the two sides of an open switch, you've got the extreme limits of the voltage you're trying to cut off. If you look at Ohm's law, you've got no current flowing through it unless there's a leak. So that means the voltage that you see here, let's say that in my case I'm looking at 230 volts. There's no drop because there's no current. So there you'll have 230 volts. There you have 230 volts. And there you have 230 volts. And then of course here you've got 0 volts because that's neutral. But until that switch is closed, you've got 230 volts anywhere at those points. So strictly speaking, I think it's actually more sensible to connect your live to the switch and your neutral to the southern and other end of the fuse. Ideally, I'd prefer this fuse to be here. So you'd have the switch. If something went wrong with the switch, it'll blow the fuse and it would not allow power to go into the radio at all. But this is the way they did it, and this is the way we have it, and this is what we have to live with. So we've got our mains coming in here. It goes through the fuse, through the primary of the transformer, and it comes out at various points depending on what your mains is. Now in my case, it's at about 230 volts. At the moment, this is set to 220. So that means that on this winding here, if I measure the resistance from this point to that point, I should get the DC resistance of this primary winding. I can go one step further. If my fuse is fine, I should be able to measure from here to there. If my switch is fine, then if I switch it on, I should be able to measure the DC resistance of the primary of that transformer simply by measuring between here and here, right? Let's try that. Let's see if our winding's fine and see what kind of resistance we get. We should get, I don't know, probably a few hundred ohms or less than 100 ohms. Now the actual switch is on there. You can actually see it from the top side, and it's activated when you activate any of the bands, and I'm just going to push any one of them. If I put off, it deactivates, but any of these will put that on. So theoretically, my switch is closed. I'm going to connect my multimeter across the prongs, and I get a very, very high resistance. Now that's not good. That's not good at all. Let me try and... That's my open. Let me close the switch. That is not good at all. That tells me that something is not connecting there. In other words, if I look at the schematic again, what I'm doing is testing between here and here. The resistance I'm trying to measure is the resistance here, through there, through there, through there, and out this side with the switch closed. And I'm getting this like an open circuit, which is not good. So I can go one step further. I can actually test different sections of this. This does not mean that the transformer is bad. It does not mean that it's bad at all. And I'll tell you why. Because if I measure from here to the fuse, it means that I've got to measure from here to one of the fuse legs. And I'm not sure which one of these goes to the fuse, but I'll try that one. See if we get lucky. And it comes to here. You see the brown wires coming in here? Let me see if it goes to there. No. Let's see if it's that one. Yes. So that's coming to there. Let me try the other one. Change this over here. See if this comes to the fuse. Yes, that's coming to the fuse. Going through the fuse. And there's my problem. One of my problems. You see this resistance running around there? That should be almost zero. And the reason is this contact here is very dirty. So we've got to clean that first. To do that is very simple. I just take the fuse out. This thing is very tight in here. This has probably been in here for some time. So it will have got corroded, grungy. Is the fuse good? Can you hear that? Yep, the fuse is good. So it's not that, it's just a question of cleaning it. And I'll use some contact cleaner here. I'll just take a cotton swab, just give it a good spray, and then go in here. It should do it. Usually it doesn't take much, and usually if you have mains applied to this, this won't happen because the higher voltage would just break across any sort of dirt that you have there. The voltage selector seems to be very well in place. It's screwed into the 220 volt pin. I'm actually going to change it to the 240, but I'll do that in a second. Let's see if we've solved the problem. Now if we do this again, between that point and this side of the fuse, we've got a short circuit. Perfect. So that line has been opened up. Now we can test to see whether the switch and the transformer itself is fine, and the way to do that is just put this on this side and we get 174 ohms. Is that correct? Well, let me see. There's something wrong with that switch. If I switch it off, I get 1.8 meg. It's not activating. Is this? Looks like our switch is dirty, but we can find out if it's a switch or the transformer quite easily. Let's go up there and I'll show you. Now we know that our mains coming in is here. It's on this brown wire. It's coming to this point here, and it's coming to this point here. And here it goes through the fuse, and then it goes into the windings. Now one of these, it should be this one, should go straight into the transformer, one side of the primary, and then that should come out here. And there it is. So our mains is coming in through there. It's going straight in there. Is that going through the switch or not? Let me switch it off. Ha! This thing's wired differently. Watch this. This is coming in here. It's going straight into the primary of the transformer. Now, according to the schematic, it should be going through the fuse or the switch before it goes to the windings. But what we've got is these are the windings. This is the 240 volt winding, 65 ohms, 220 volt winding, 55, 26, 16, and the 110 volt winding, 14 ohms. So it's going straight in there. Then it should be coming through to here. And let's put it on. And now we're getting 100 ohms. This is now giving us a reading through the switch. The switch is dirty, and that's why we're not getting any reading, or getting a different reading. Here we've got 98K. This thing's giving us strange readings because the switch is not clean. So I'm going to give it a good blast of contact cleaner. Usually the contact cleaner gets into the switch, and we should be able to sort that out. Let's just check what we do get. We should get 65 ohms or so on the highest winding, and the one that we've wired up is actually 60, well, it's jumping around because again 58 ohms on the 220 volt winding. Let me clean the switch and see what we get next. Here's the switch on the top side. Now, getting contact cleaner into the switch is not as easy as it is with some of the other components. Sometimes there's an opening on here, and you can, I think there is an opening there and there. So I've sprayed contact cleaner, and now I'm just going to keep activating it. Give it a bit of time. With contact cleaner, you've got to do it a few times because the first time, the second time, it just sort of loosens the dirt, but it doesn't really wash it away. It doesn't matter which one I activate it with, it does the same thing, as you can probably see. And now, if we look at our multimeter, we're getting something that looks right. That's off. Still acting up. But there's our 58 ohms. Well, not really. There's our 59 ohms, and it'll get better as we keep activating it. But now we've got that circuit checked, and it seems to be fine. That switch will need to be cleaned a few more times, but remember, when you're using mains on here, it'll break straight through, and we won't have this issue. But it looks like it's holding. Yep, it's consistent. So what we've done is we've actually checked continuity between this point and that point on the mains plug, and it's going through the fuse, through the switch, through the primary, and we're getting more or less what we expect. This is going to be a few ohms off because of the dirt that might be on the plug, some of it still on the fuse holder, some of it on the actual switch, but we can now do a little bit of painting on that drawing, which is something that if you know me, you know I like to do. And it means that I can actually paint in what I've already checked, which is from here to the primary, through the primary, at least to that winding over here, to the switch, and then through the switch to the other mains prong. We've done some painting. Isn't that great? Yay. Okay, that's the first stage done. It does not tell us that the transformer is fine, but it does tell us that the primary of the transformer seems to be intact for now. You know, while we're here, we might as well check the other windings of the transformer, and we've got two more. One is the secondary for the heater winding. That's over here, which then comes down and feeds the dial lamps and the heaters. And the other one, of course, is the secondary itself. Let's look at this one because it's actually a lot simpler. What I've done here is I've removed all the tubes from the radio, including the magic eye, which I generally tend to forget, which means that the secondary winding is now supplying nothing as far as the tube heaters are concerned. And I've also removed the dial lamps. There are two of them. Now, what is the heater winding supplying in this circumstance? Well, in this case, the heater winding is supplying absolutely nothing. If we've removed the heaters, which are those things over there, drawn on this schematic, and if you remove the two dial lamps, the heater winding, this thing here, or actually this thing here, is simply connected to ground and going nowhere. So if we measure from ground, remember this winding over here is actually connected to ground on the side, so our ground of the heater supply is the chassis itself, and we measure to the other side, we are getting the DC resistance of this path over here, nothing else, or we should be getting nothing else. So where are we going to measure that? Well, we can measure that in a few places. We can actually measure across the dial lamp, or we can go to one of the tube pins and measure the heater winding pins on the tube itself. And the easiest one to get to is actually here on the ECH81. If we look at the board itself, here's the ECH81, that's the EF89. If we look at this one itself, we look at the heater windings, it's pin 4 and 5. We've actually got another tube here, there's the EF89, and we know that that one conveniently is also pin 4 and 5. So let's measure between 4 and 5. Now, when you look at the top, the pins are counterclockwise. If you're looking at it from the top, this is 1, 2, 3, 4, etc. If you're looking on the underside, of course, it's the other way around. But this is pin 1, 2, 3, 4. And if I measure between 4 and 5, what do I get? 0.5 ohms, 0.4 ohms, 0.3 ohms. That is the DC resistance of the heater windings. Let's look at this one as well, just to double check. There's 1, 2, 3, 4, and 5. There we go, 0.4 ohms. I can actually just go to the dial lamps and do the same thing, and I should get exactly the same thing, or damn close, because I've got wires going around. So we have checked that our heater supply, the DC resistance of the heater supply, seems to be fine. So we can actually come here and paint this up because we have checked it. That winding seems to be okay, and that means that, well, if you really want to get painty on here, this is what you do. We know that that is fine. We still don't know that the heaters themselves are fine, but we leave it like that. So that has been done, that's been checked. Now we have one more winding, and that is this guy over here. By the way, while we're here, we did check that these windings were fine as well. Remember, I measured resistance in those, and they all seem to be okay. They were giving me different resistances, so although I'm not going to use this, I can actually mark this as checked, and that's where we are right now. So now we want to measure this winding. This is one of the most important ones, and the way to do that is actually quite simple. Again, we've got 2 points that we can look at. We can look at the AC lines, the AC inputs, that one and that one, of the selenium rectifier. That's all we really have to go on. And let me show you where we find that. As I showed you from the other side, this is the selenium rectifier. And here we've got the negative, the positive, and the two center ones are the AC in, and the AC in is actually where the secondary of the transformer goes. So if we measure that, we've got 137 ohms, and that sounds about right. Good. So we can now mark that in, that section there, that winding, as intact. All we've done so far, believe it or not, is to determine that the three windings of the power transformer, the primary, the secondary, and the heater windings, are intact. We've also gone a bit further. We've made sure that the path from the mains plug is actually clean all the way through. In other words, we've cleaned up the switch, we've cleaned up the fuse contacts, we know the fuse is fine. So that is all we've done. And now we've got to start working on the actual core components. And there is actually one simple test we can do here without actually activating the high voltages to check whether the transformer is doing its job. And I've done a video on this before, focusing purely on how to test out the power transformer safely. But I'm just going to show you what I do here. And basically what I'm going to do is I'm going to feed an AC voltage on here, right there, and see what happens at this point and also at this point. Now I'm not going to supply mains because the whole point is to try and keep this whole thing safe for now. So I'm going to choose a low voltage AC and see if I can detect the voltage on this end and that end. And the voltage that I'm going to apply here, the signal I'm going to apply here, is actually from my signal generator. So here's the signal generator, and I've got this thing set to a frequency of 50 Hertz. So I'm sort of imitating a mains frequency, but I'm going to give it 1 volt. 1 volt RMS, feed it in. And where do I feed it to? Well, straight into the plug, as if this was mains, okay? And at this end, I'm going to measure the input to the selenium rectifier. In other words, I'm going to measure between here and there. I've got the multimeter on AC volts, and I have got 1 volt over there already. Now I've got these switches on and everything because you've got to pretend this is mains coming in. But if I switch off the signal generator, that goes down to 0. If I switch it on, I'm feeding 1 volt and I'm getting 1.1. Does that tell me much? Well, actually it does. It's a low voltage, but it's producing a ratio of 1 to 1.1. In other words, 1 volt in is producing 1.1 volts out. What happens if I up the voltage on the signal generator to 2 volts? 2.2. The same proportion, 3 volts. 3.3. So you see, this is showing me that the transformer is doing its job. It's converting an input voltage in AC, an AC input voltage, of 4 volts RMS, and it's producing 4.4, 4.5 on the output. Still AC because I'm measuring at the point where the secondary of the transformer connects to the selenium rectifier. I'm not worried about the DC being produced by the rectifier because at this point, at such low voltages coming in, it's probably not producing anything yet. The selenium rectifier requires higher voltage than normal silicon diodes, which would require about 0.5, 0.6, 0.7. But I'm only interested on the transformer action, and that's doing the job. Okay? Now, I can go up 5, or 6 rather, 7. I think this is about as high as my signal generator can go to. And I'm getting my same ratio coming out the other end. So the secondary seems to be doing its job. But I can also test the heater voltage to make sure that that is working as well. And to test that, I'm just going to connect it to one of the dial lamps and see what we get out there. Now at the moment I've got this on 7 volts and I'm getting 0.22. Let me go down to 6. It's going down. That's 0.19. If I go down to half of that, 3, 0.09, 0.09 something. So again, that's doing the same thing. And I'm getting approximately the same proportion, about 34, what is that, 30 millivolts per volt. Take that to 2, 60. Now you don't have to worry too much about the actual ratio. Remember, this thing is a signal generators can produce very low currents. It's not a strong source, so any losses that happen there will have an effect on the on the result. But the point is, our transformer seems to be working as a transformer. So I'm comfortable to carry on now with what I want to do next, which is the selenium rectifier. First thing we need to do is desolder the connections to and from the selenium rectifier, which is this thing over here. There are 4 connections. This red one here is the positive out, and we know that because it's going to the first filter capacitor over here. This one here is the ground, and we know that because it's going to a ground pin on there on the chassis. So the 2 extremes are ground and positive, which means the 2 middle ones are the input from the secondary of the power transformer. So let's just desolder that. I'm not too worried about damaging that itself because I'm going to use something else completely, but I do want to protect these wires coming from the transformer. Okay, we've desoldered them. Now we just need to remove the selenium rectifier from the chassis. And in this case, it just takes 2 screws, that one and that one. And we should be able to do it if I can get the screwdriver in here. There we go. That's out. Now, if you haven't seen one of these, this is what it looks like. It's just a bridge rectifier. Effectively, what this has got inside is 4 diodes. The difference is that they are selenium diodes rather than silicon diodes, but this thing's completely closed. You can actually remove it by putting a screwdriver in there and this whole thing comes out. But these pins over here are marked, and you can see that it says AC. Can you see that? AC symbol, AC symbol. Those are the 2 central ones. There's the positive over there, and there's the negative over there. The other thing we need to know about this is that it is rated for the 200 and something volts that we are getting coming in here. So we're getting about, what did we see? It was about 1.1 ratio of input to output, or output to input. So if we've got 230 volts coming in here, if we maintain the same ratio, it's about 250 volts AC coming out of the secondary, which is what this thing will see. Now these things are normally rated a bit higher than that, probably. I'm trying to see if there's any rating on here. But this is usually about 350 volts, and these things are rated for about probably 100 milliamps, 150 milliamps, not more than that. So something this size is actually not that fantastic compared to what we can get today. Now, I've done this restoration many times in various ways. Originally what I did is I actually ripped this out, pulled this out, and as I said, you can do that. I think I can just show you there's an indent there. So you can just put a screwdriver in there and you can pry it out. Same on that side. This whole thing comes out, and you can actually put 4 diodes in here. You can actually build a 4 diode bridge rectifier, 1 amp or something, so they're way overrated, but they're small and they can very easily fit in here. So if you want to maintain the absolute exact same look, you pull the guts out, you take out all the little pieces of selenium and everything else that's in there. There's a lot of little discs. Throw that away. There's a plastic former, and you can do that. And I've done a video, I think, in which I do it that way. But since I've decided to change my tactics, because this is a huge job, it really is far more work than it's worth. And I've actually had a little board done, designed to fit 4 diodes on there, and also some resistors. Now, why do we need resistors? Well, you may know that when we have a bridge rectifier like this, you have AC coming in, DC going out. Now, what values are we going to get across this bridge rectifier? Well, if we have, for example, 230 volts coming in, this is volts AC coming from our transformer. It's probably more like 250, but let's call it 230 volts coming from the secondary of our transformer. V out should be 230 times 1.414 minus 1.4 volts, which is approximately 325 volts DC minus 1.4 volts DC, which is approximately 323. Okay? That's what you'd normally get with a normal silicon bridge rectifier. Silicon diodes that have a drop of approximately 0.7 volts each across each of the diodes. All right. The reason is what you've got coming in here is sinusoidal waveform at 50 hertz. In my case, it would be 60 hertz in the States. And what you've got coming out here is this. Across the zero line, and that is your peak voltage, which is basically that. What happens with a selenium rectifier is slightly different. The difference is that you've still got 4 diodes, but the drop is not 1.4. The drop can be like 20 volts, 25 volts, 15 volts, depending on the voltage and the current. That drop is much, much higher. So what you will see here in the case of the selenium rectifier is not 323, but it could be like, let's call it 293. Which means you've got a drop. We're showing a drop here of about 30 volts. That is not unreasonable. And the problem is this drop gets higher and higher as the selenium rectifier gets older, because it creates a lot of heat inside. It deteriorates the components, and it makes the drop bigger. And because you've got a voltage drop across a component, that current is flowing through, it means you've got power dissipation. The more power you dissipate, the hotter it gets. The hotter it gets, the more it deteriorates. You see where I'm going, right? This thing's just going to spin out of control. Sooner or later, that selenium rectifier will blow up. Now, with silicon diodes, as we've got here, this thing can handle a hell of a lot of voltage, hell of a lot of current. If I use 1N4007s, just off the top of my head, the rating for those are over reverse voltage is over 1000 volts, and I believe it's about 1 amp. So this is more than enough for what we will need. However, we've got a problem, which is that difference in voltage. And the way to overcome that is actually to put a resistor in here. Since the drop is not happening within the rectifier, you create another source or another point where the voltage will drop as the current flows through. Call that I. And in our case, it's about 100 milliamps. I think that's about the max that this thing pulls, is about 100 milliamps. So as the current starts flowing through there, 100 milliamps through that resistor creates a voltage drop, and therefore you will drop from your 323 when there's no current to, let's call it 290, 293 volts when you've got current. I'm showing here a drop of 30 volts, which in this case, if we look at 30 volts on, let's see, 30 volts across with 100 milliamps, you've got to remember the most important theory in this hobby, and that is V equals IR, and power equals voltage times current, or equals V squared over R, or equals I squared times R. Whichever way you look at it, those are practically the only formulas you'll ever use in restoration, just about. And what we find is if we want to drop 30 volts with 100 milliamp current, that resistor's got to be 300 ohms. And what sort of power is that going to dissipate? Well, if we've got 30 volts and we've got current of 30 milliamps, power equals voltage times current. So voltage is 30 volts times current is 0.1 amps, so power is 3 watts. That would be a typical resistor that you would use to drop the voltage there. Here's the problem. We don't know what that current will be till we've restored our radio, because whatever current we measure now is dependent on the voltage drop that this thing's already creating, the original selenium rectifier is creating, and it's also dependent on the current draw that the existing components are creating from the supply, from the B+. Now, when you restore it, that current can change. It can drive a tube hotter, which means the current will increase. It can have less leakage, which means the current will decrease. So you don't really know what resistor to put in here till the end, and even then what I normally do is it's a trial and error thing. I have 3 resistors, I've got space for 3 resistors on that board. So I've created a board where I've got space for 3 resistors in parallel. And what I've done is I've made them accessible from the top, so that once you've got that board in place, you can actually solder those resistors in. And the reason I have 3 is that sometimes, like 300 ohms, you don't have resistors that are 300 ohms. If you find that what you need is 300 ohms, because you're using a decade resistor box or something similar, and you want to create 300 ohms from putting resistors in parallel, well, it's not so easy. But what I would do here, for example, is I would put I'd put 3 1K resistors. That comes out at 330 ohms. I'd use 2 watt resistors, which means I'd get 6 watt dissipation, because the current that goes from here to there would split evenly through those resistors as they are equal. The dissipation is the cumulative amount of the individual dissipation capability, so 2 watts, 2 watts, 2 watts, and therefore I'd have 6 watt capability, and this thing would work great. The voltage would probably be slightly different, but this is tube stuff. You don't need to be, accurate to 0.1 volts. If you are 5 volts above or below, it's not a big deal. So that's how I designed that board, and that's how I would go about creating or testing for what resistors I will need on there at the end, the last stage of the restoration. What I do at this stage is I build up the board with 4 diodes, 4 1N4007s. I leave this shorted, so I put a wire from there to there on one of the holes for the resistors. So I short it out, which means that the entire B plus that's being created here without that big selenium voltage drop will go through. But until the end, I'm using this on dim bulb, and I can restrict the voltage anyway with the dim bulb tester and also with the Variac. So I'm not too worried about that initially. I wait till the end, and then I take that jumper out, the short, and I play around with resistors to get the value that I need there, and you'll see me doing that later on in the restoration process. These are the new boards. Now, this thing here is actually to replace a filter capacitor, so we don't really use that one. That's for the next stage. But this is what I replace that with. Now, if I did this right, and it did, see, the holes fit exactly. So the idea is that I can do this, I can take this board, I can put in 4 diodes. There's the marking for the 4 silicon diodes. There's my one ACN, there's the other ACN. This one has not got the connections at the end like this one does, because there's actually one of these, a Siemens one, a Siemens version, where they are on opposite sides, and it's more common than the AEG version, but it doesn't matter. As long as you connect the wires from the transformer secondary to there and to there, you get your positive out there, your negative out there. And because of the spacing of the holes, exactly the same as that, fortunately these are the same as the Siemens ones, I can just put some spaces there, and this thing will fit nicely exactly on the same spot using the same holes as the original was held in with. What I meant by tacking resistors on is these resistors are facing outwards, so I can just tack a bigger resistor across here even when that's in place, and then once I know what I want, what value I want, I choose 2 or 3 resistors. I cut down the legs to size, and I just solder them from the top end. I don't really need to go to the underside to solder that in. I can do it from there because the pads go right through, and it's on both sides actually, so it makes it a lot easier. So I'm going to do that. I'll build this up, put it in there, and we'll carry on. And there we have it. It's connected in place with some nylon separators, right, to keep it away from the chassis. You do not want any of this to touch the chassis, or you'll have a short circuit, obviously. This thing is full of high voltages, and here again, another warning. If you're playing with this stuff, be careful. You've got to know what you're doing, otherwise stay away from it. This can kill you. There are high voltages, there will be high voltages all over the place. And what I've done at the moment, you can see this short circuit over here, this little little connector here. It's just a piece of wire connecting across the resistors. So I'm effectively giving it zero resistance to the end, which means that the full B plus that's produced by those diodes will be passed on when I connect it to the filter capacitor, which I haven't done yet because we still need to replace that. So that's it. That's how it works. And you can actually get to these points here quite easily from the underside. So you can see that when I want to put resistors in here, it won't be a big issue. I've just got to make sure the resistors legs do not go through the holes and deeply into the chassis, because if it touches the back, that'll be a short. And here's what it looks like with the AC connections made. I've put them through the underside, or rather behind the board. So the yellow one went to the bottom AC pin over there, and the red one had to go to the top. And to do that, I had to extend it a bit. So I put a bit of red wire, bit of heat shrink. It goes through the back and comes out the top here. So our secondary of the transformer is already soldered in here. And all we need to do then is to connect the ground and the positive once we've worked on the filter capacitor. And that's where I'm going to leave you for now, because this thing takes an enormous amount of work to prepare, and this video is going on for ages. So I'm going to leave you for now. When we carry on next time, we'll be looking at the filter capacitor and then checking the B plus pathways through the entire circuit, and I'll show you exactly how I do that. So for now, I hope you've enjoyed this, and if you have, click like, share, subscribe, and all that jazz. And if you want to support the channel directly, you can do so on Patreon and PayPal. Links are in the description below. Once again, thanks for watching. Bye for now, and most of all, stay safe.